It's a great pleasure for me to introduce Sebastien Ducruix from École Centrale in Paris, who has made it all the way here from Paris, despite some challenging journey, which involved a strike of French pilots,
yes.
And his flight was cancelled at short notice, so he quickly switched to train and just about made it, and he has to dash off very soon. So if you have any questions for him, don't hang around, he'll have to leave at lunchtime. But I don't want to take any more of your time, just introduce the title of your talk. This is Theoretical Determination of Flame Transfer Function using the G equation, comparison with experiments. Sebastien, please.
Thank you. So first I'm very happy to be there, in spite of all the disagreements on the way. This is a work that has been mainly performed at the lab, even if, of course, I will also include some parts coming from other studies. And there's only my name on this slide, but this is a teamwork, and you will some of you will recognize work coming from other colleagues from EM2C and elsewhere. So I was not sure I would do that, but finally I decided to put a few slides about the background and the motivations, because it's, even if we spend only a few minutes on it, it's always a good thing to have everybody prepared for the following of it. The motivation is the following. Thermoacoustics and combustion instabilities are one of the major problems that are encountered while designing new systems, new propulsion systems, for example, rocket motors, jet engines, or ground gas turbines for electricity production, furnaces. And they are usually characterized by large flow oscillations. And those flow oscillations, they will have consequences that can be very various. That could be an increase in the radiated noise. You can get heat flux increase, structural vibrations, and worse than that, you can get extinction or flashback, the flame propagating in the upstream part of the system and destroying it. This is something that can be very complicated to deal with. Maybe I should show this picture right now. This is a view of a swirler that was meant to deal with pure oxygen and fuel, but in that case temperatures are so high that when you have flashback, the metal part melt, they purely melt due to the instability. So, there are a few branches in terms of research. The first one is the more fundamental one, and this is the one we are going to be interested with today mainly. This is understanding the fundamental mechanisms of dynamic interactions. And we need that to do the rest of it, and the rest being, trying to describe and predict the instabilities in complex geometries, and also develop, if necessary, passive and active control methods. So I will mainly focus on the understanding today, but we are also working hard on those two areas. On a very simplistical point of view, this is how you could represent things. You have the flow interacting with the combustion process. Okay, so this is more the mechanical part, and this is more the chemistry part, but they are closely linked. And at one point you have perturbations coming in the system. So for example, you can have acoustically induced forcing, which means that you will perturb the system upstream by pressure or velocity fluctuations, usually velocity fluctuation, and this will cause a fluctuation in the heat release rate. And this is the part that we will be discussing today. But what's also interesting is that having unsteady heat release will cause pressure fluctuations, acoustic pressure fluctuations. This is what we call usually combustion noise. And this noise may interact again with the perturbations that are here, because you all know that acoustic waves are associated with velocity and pressure fluctuations. So if you have a coupling here between the velocity and the pressure fluctuations, you may have combustion instabilities, and this is more or less a question of phase match. I won't go into the details because this is not the objective today, but if you get this, you have the main, a rough picture of it. What will be the content of the presentation then? I will start with the description of a simple model derived from the G equation to try to deal with the flame response to acoustic modulation. This model will be compared to experiments, and you will see that it has some good properties, but it's not dealing with the results very well, the model. So we will go to G equation calculations, and we will have to look at the velocity fields to see what's going on, and I'll give a few perspectives in the conclusion. But before doing so, we need to define exactly what we want in terms of flame response to acoustic modulations. And to do so, I will not derive the whole equation. I will just put one result, but I wanted the assumptions to be clear. So those assumptions are here. Some of them are affordable, other ones can be discussed. It really depends on the situation where you are, and sometimes you don't have a low speed, sometimes gamma is varying a lot, and so on. But if you make all those assumptions, then you can go to the following equation, which seems a bit difficult, but it's not, because it's a wave-like equation. On the left side, you recognize what you usually get for wave propagation, and on the right side, I only kept two terms. So it was my choice. You have more terms than that, but I only kept two terms. One is associated, I would say, what is associated with the flow, or with the turbulence, if you like, and one is associated with the combustion process. And if you look closer to this particular term, what you can see is that it can be rewritten if you assume a single reaction step and equal CPs. Then you will get this formulation here with gamma, the formation enthalpy per unit mass of the mixture you are burning, and the reaction rate. Okay, and gamma is usually not varying or not that much, so you can put it away. And then what you will get inside the temporal variation is the unsteady rate of heat release per unit mass. So this is an important result. This is what we are going to be looking for in the rest of the presentation, is what's happening in terms of non-steady rate of heat release. Okay, this is our objective, trying to define and measure and model the non-steady rate of heat release per unit mass of fuel. There is another way to get that, so I put only one slide so that you can have a look at it by yourself. You can also look at the acoustic energy budget in the system. So you need to make some assumptions too if you want a simple results, but you can also deal with more complicated assumptions. If you neglect dissipation terms, and if you assume that you have low Mach numbers, so a slow flow, then you can use this definition for the acoustic energy density. And if you make if you average the equations, what you get is that the variation of acoustic energy will be associated with two terms. One is what you usually call the Rayleigh source term, which is a product of P prime and Q prime. This is why you need those two terms to be in phase, more or less. And minus the acoustic fluxes at the boundaries. So if I look at this scheme here, which is a very simple one, you will get a term here that can be either positive or negative depending on the phase between P prime and Q prime, and the fluxes at the boundaries. And the budget will be positive or negative depending on those two terms. But what's interesting here is that, once again, the important thing concerning combustion is properly defining, measuring, or modeling the unsteady release of heat. Okay? This is what you need. And this is what we're going to do in the following steps. Okay? So this is a simple way to look at it. If I want to go a step further and say, okay, what could be those fluctuations and where could they be coming from? There is a nice drawing from Ducruix a few years back, and you see that even for premixed systems, this can be quite complicated, because those fluctuations of heat release you are looking for, they can be associated with the flow and its turbulence, the flow instabilities, equivalence ratio fluctuations. So for those of you who are not completely familiar with combustion, equivalence ratio is the mixing process that will exist before combustion. And I will, in the following, I may be talking about lean flame. It will mean that we are below stoichiometry, and rich flames we are above stoichiometry. Okay, so if the mixing is fluctuating, then the heat release will be fluctuating too. And all those fluctuations, they can be coming from air and fuel supply, and the fluctuations coming from the air and fuel supply, they can be coming from entropy waves or acoustic waves in the combustion chambers. And so you have a a very complicated drawing here showing you that there might be several reasons for the heat release to be fluctuating. Sorry. So I will show you a few driving processes. We are still in the idea that we need to look at combustion instabilities by looking at the unsteady rate of heat release. What are the driving processes? The driving processes can be very fundamental. Huh? If you look at strained flames, like this is the case here, so this one is non-premixed and this one is premixed, and then if the strain rate is fluctuating, then you will have a fluctuation of heat release associated to this fluctuation of strain. If you have vortices in the flow, which is often the case, those vortices will be interacting with the flame, and you will have fluctuation of heat release associated with this vortex passing through the flame. And once again, if you have mixture fluctuations in the flow, those mixture fluctuations will interact with the flame, and there will be a heat release fluctuation associated with the equivalence ratio fluctuation. Okay, so all those phenomena can be encountered, but one of the big issues with this field of research is that you never know which one is going to be there or not, and you have to try to guess what's going to happen in terms of interaction with the flame, between the flame, the acoustics, and the flow. So we've been working on very fundamental experiments to try to investigate those driving processes, and I will show today one of those, which is the one here. This is the case of acoustically modulated flames. So I won't go into the detail right now because I have a slide explaining how it's going to work, but the idea is to induce artificially the perturbation and to control it, and to see how the flame is responding to this perturbation. And if you do so in a particular framework, you can get what you will call the flame response to the perturbation, which is what you need. In the following, it will be called the flame transfer function. I will explain a little bit what's the idea, but more or less the idea is to understand how the flame will behave when it is modulated from upstream. Okay. There's another way, and this is about the end of the context. There's another way of describing this, which is the following one. So you have a typical instability mechanism will involve the flow, the combustion process, and the feedback process, which is usually the propagation of acoustic waves upstream. And you need to model this, so you will need a flow solver. You need to make flow assumptions. You need a combustion model, and you need acoustic resolution if the acoustic is involved in the feedback process. Now, if you want to look at flame response and flame transfer function, what you're doing is, compared to the typical instability mechanism, this is as if you were breaking this arrow here, and you force by yourself the system, by a specific way, and this forcing is coming in the flow, modify the flame, and you measure the response of the flame to this modification. And this is what you will call flame transfer function when you are doing linear assumptions. And you can also work with a more general framework, which is a flame describing function, FDF, if you are also looking at the way the amplitude of the forcing will perturb the system. But if you are not looking at this particular point, dealing with the frequency, different frequencies will give you the response of the flame as a function of those frequencies, and this is the flame transfer function. Okay. Another way to look at it, if I take back the first one of the first slides, is to say, okay, I'm not interested in this feedback process. I'm only looking at that one. Okay, acoustically induced forcing. Is it okay with everybody? So we can now start, I would say, with the study. So the idea is to develop a model for laminar cases. There are various reasons for that. I was about to say 2 reasons, but there are various reasons for that. Here, there will be 2 reasons. The first one is that it's a very pedagogical case, and you can learn a lot of things with it. And also, there's another reason for that, is that it's a situation where you can clearly and very easily compare experiments to the modeling. So you can see if what you're doing is right or wrong. So the experiments is the following. You have a Bunsen-like flame. It's a conical flame, so it's not the case here because it's already modulated, but it's a conical flame, and you can adjust the acoustic modulation coming from upstream with a very wide frequency range, typically from very low frequencies to frequencies of about a few hundred hertz, and you look at what's happening to the flame using diagnostics that are able to give you the unsteady rate of heat release I was mentioning. And in parallel, you can develop modeling. So this modeling is based on a description by Flayfield and co-authors. This is the Goniem team in MIT. And the idea is to look at the flame as a thin surface and see how this surface is wrinkled by the perturbation coming from upstream. Okay? And we must not forget the target. The target is the flame transfer function. The flame transfer function will be defined here as the ratio between the unsteady heat release rate divided by the mean heat release rate. and you do that to have a non-dimensionalized quantity that can be compared to other situations. And you want this ratio to be a function of the ratio between fluctuations of velocity, v1 here, and mean velocity. In the following, the subscript 1 will be associated with fluctuations, obviously, and the subscript 0 with mean situation. So if we want to develop this model, we will make a few assumptions that may not be necessary in the general case, but that are necessary here if you want to derive the model until the end. We will assume that the flame burning velocity is constant, which may be a big assumption sometime. I can explain in the following if you want. We will assume that the axial velocity that the velocity field in the fresh gases is axial. You don't have any radial contribution. And we will also assume that the velocity field is spatially uniform in the fresh gases. Okay? You need those three assumptions to go further in the model. So we are starting with from the G equation. So G is supposed to be a given surface, and you can write the variation of G as a function of the flow and the flame. And this is what is written here. So the objective, sorry, here is not to explain this equation. I will take it as a starting point, but we can discuss the assumptions that are associated with it. V is the velocity vector, and SL is the laminar flame displacement speed. I will introduce eta as this equation. G is equal to eta minus y. Y is the axial axis. Okay, so eta is here, and you have eta 0, of course, obviously, and you will have eta 1 also. So introducing eta in this equation, you get the following one, which is it's not very complicated to go from that one to this one. You can have a look at the publications, it's quite easy. And then, it's usually the case, you assume that you are going to look at small perturbations. So eta 1 will be small compared to eta 0. And doing so, you introduce this into this equation, and you only keep order 1 terms, and you get a very simple equation, a very simple differential equation between eta 1 and v1. There's a mistake here. There's a dr that should remain, so I'll correct it and give you the proper formula next. I've written this too fast. Still, the last result is correct, but there's a mistake here. So you have an equation for eta 1. Eta 1 is the way the perturbation propagates along the front here. But this is not what's interesting you. You want to access Q1, which is the unsteady rate of heat release. So to do so, you need to introduce a first term, which is the area fluctuation. You can calculate this area fluctuation depending on the fluctuation of the line eta 1, and this is a relation that links A1, the area fluctuation. So you can imagine a cone, and this is the fluctuation of the cone. So A1 of the cone surface, A1 is fluctuating like this as a function of eta 1. Alpha 0, sorry I didn't introduce alpha 0. Alpha 0 is the cone angle, the steady cone angle. Half angle. And you can relate the heat release fluctuations to the surface fluctuation. So this is the case because we are in a premixed situation. In a premixed situation, if you are below a stoichiometry, the heat release fluctuations are exactly proportional to the surface fluctuation. The more surface you have, the more you burn. The less surface you have, the less you burn. Okay, and the proportional factor is this one here. Okay. So you first introduce A1. You use this equation to find an equation for A1. I skipped that part. It's in the publications. And then it's very easy to go from A1 to Q1 because you only have this factor to be introduced. And after a few derivations, which are not that easy, they involve Laplace transform and so on, but it's still affordable. You get the following relation. You can write Q1 over Q0, which was the objective, as a function of V1, as a function of the ratio V1 between V1 and V0. And the relation between those two terms is associated with this term. So it may look a bit complicated, but it's not actually. And it introduces a relevant parameter, which is a reduced frequency. The frequency is omega here, and it's present here and there. But you also have a reduced frequency, which is proportional to the frequency, but which introduces a geometry parameter, which is typically R, a chemistry parameter, which is SL, and a parameter that is associated with both, which is alpha 0. Alpha 0 is associated with the chemistry and the flow because alpha 0 is associated with the fact that the flame will propagate against the flow, and the angle here will be a kind of balance between the flame speed and the flow speed. Okay, so it's both a chemistry and geometry parameter. So this is a nice result, but it's not very easy to see what's happening. If I give you this function, you are not able to draw it very easily. So the best way is to do it, and we will do it in two steps. We will first look at the amplitude of this function as a function of the frequency of the reduced frequency, sorry, and we will then look at the phase. So first the amplitude. The amplitude is the following. It's given here. The formulation is given here, and we plot as a function of the reduced frequency. So the reduced frequency is varying from 1 to 100 here, and the flame transfer function amplitude is varying from a little bit less than 1, it should be 1 here, and it's decreasing to 0. Okay, so you have a behavior that looks like a low-pass filter. This is a very typical result in combustion. Most of the flames, not all of them unfortunately, but most of the flames, they behave like this. They behave like low-pass filter, meaning that if they are perturbed by a low-frequency perturbation, they will follow this perturbation. But the higher the frequency, the lower the response of the flame. Okay. What's also interesting is to introduce a first-order system, a first-order set of equations. Usually you have a parameter in those first-order systems, and if you use a first-order system parameter beta equal to 3, you get a representation, a simplified representation of your model. Okay? Why is it interesting? Because it's very easy to calculate first-order systems. So this first-order system is not very far from what you got from the simple model you just derived. In terms of phase, this is what's happening. So you have the real phase here, the phase associated with the model here. So it starts somewhere there, and then it saturates around pi over 2 actually, with oscillations. And if you use the same first-order system with the same parameter beta equal to 3, you have something that is not very far from this behavior. Okay, you don't get those oscillations, but you get the proper starting point and the proper end point. Okay. So this was derived from the G equation, making strong assumptions, and it is now time to challenge those assumptions using an experimental configuration. This is the experimental configuration we are looking at. It's a very simplified one, but it's perfectly controlled, and there is a wide range of frequencies and amplitudes of modulation that are available. So the flame is a conical Bunsen flame. It's stabilized here. You can have different diameters to change the cone and the cone angle. And the modulation will be induced by the loudspeaker that is placed at the bottom of the burner, which is here. And if you remember well, you need two quantities. You need the fluctuation of heat release, and you need the fluctuation of velocity. Fluctuations of heat release will be in a very simple way measured using a photomultiplier plus a filter which is associated with the radical CH spontaneous emission. You can quite easily show that in the case of perfectly premixed flames, there is a proportionality factor, which is almost perfect, between this emission and the heat release. So you don't get the absolute quantity, but you can easily get the relative quantity, which is Q1 over Q0, by measuring I1, the intensity, over the intensity fluctuation, over I0, the mean intensity. So we will access the unsteady heat release by this way. And we will look at the velocity fluctuation using a laser Doppler velocimetry system. You seed the flow with particles, and you have two coherent laser beams crossing each other, and you create fringes here, interference fringes. And while the droplets are crossing those fringes, the light emission is modified, and depending on this light emission modification, you have access to the velocity. I cannot go to the details, obviously, right now, but if you need more information, I will give you with pleasure. So you have access to Q1 over Q0 experimentally by I1 over I0 and V1 over V0. So you can build this transfer function experimentally. But let's have a look at what's happening on the flame first using a Schlieren technique. So I will not detail the Schlieren technique. I won't explain how we get those beautiful colors, but once again you can ask questions. The stoichiometry, the equivalence ratio is 0.95, so we are very close to stoichiometry, but there's an excess of air. All the fuel is burned. This is methane. The main velocity, bulk velocity here is about 1 meter per second, and the reduced frequency is 5. So if I remember well, if you want to get the real frequency, the real frequency in hertz, you have to multiply by 5. Okay? So reduced frequency of 5 is a real frequency of 25 hertz. Okay? Just need to multiply by about 5 and you'll get the real frequency. The frequency we actually put in the system. So this is the way this one is modulated. So you have a bulk modulation, ondulation, and you feel that your assumptions may not be too crude. It seems okay. Now, if you look at what's happening in the same situation, but with a reduced frequency multiplied by 3, meaning you are now with a reduced frequency of 15, the situation is completely different. And you will get what we now call the pagoda flame, which is a flame looking like a pagoda. And you have perturbations. You have perturbation coming from the bottom of the flame. Oh, okay, I see what's happening. If I touch this, it stops the movie. So I cannot show you this way. You have a perturbation coming from the bottom of the flame, and which is propagating along the frame front, which was not really the case in the case before. If I look at instantaneous images, this is what you get at omega star equal to 5, and this is what you get at omega star equal to 15. If you now look at the signals they are quite satisfying. We can play with the velocity fluctuation range between 8 and 20%. We can play with the frequency between 5 and 300, 400, 500 Hertz if necessary. This gives a reduced frequency of 1 to 60 for the small burner and 1.7 to 100 for the large burner. But what's interesting is here. You see that as a function of time, we draw the intensity fluctuations here and the velocity fluctuations. So those are resolved data. And you see that it's not perfectly sinusoidal, but it's almost perfectly sinusoidal, meaning that you will be able to make the assumption that most of the response are associated with the main modulation frequency. You have negligible harmonics. And now, if I'm thinking again about the flame transfer function, what it is, finally, this is the amplitude of the flame transfer function will be given by the ratio of amplitude between those two quantities, and the phase will simply be given by the difference between the maxima, for example, here, or the minima, or when you go through zero, okay? You have the amplitude and the phase for a given frequency. I don't remember which one was given here, but for this particular frequency, you have access very easily to the amplitude and the phase of the transfer function. So it's now time to do it. And I've put on this slide describing the amplitude of the transfer function as a function of the reduced frequency, several cases associated to different mean velocity to see if there was an influence of this quantity on the result. And I've put F, which is my simple model here with the black line, and H, which is associated with the first order system I was mentioning before. And what you see in terms of amplitudes is that we are not that bad. We are starting more or less at the proper position, and the model follow properly the curves. And you see that around 10 there are some discrepancies that are not caught by the models. And also, while all the curves could fit collapse on a single curve at the beginning due to the use of the reduced frequency, it's not the case anymore after omega star equal to 10. Okay? So we're not very bad at representing properly the flame transfer function with our simple models for this area. There are some bad news. The bad news are associated with the flame transfer function phase. So you have here the two models, the one associated with the simple model we derived and the first order model. So we are good at maybe omega star equal 1 to 2 or 3. 1 to 2, 3 is there, so even at 3 we are not good. But afterwards it's not the case anymore. And what you see is that all curve collapse until 3 or 4, but then afterwards there is the same trend as for the amplitude. This is not universal anymore. Omega star is not representing properly the phase anymore, and second consequence is that this is not good at all. Okay? So you need to work on that. So there is a first preliminary conclusion here. We have a good modeling behavior for the amplitude, so 6, even larger values than that, and 2 for the phase. But we underestimate, there is an underestimation for intermediate frequency, which may be due to too strong assumptions. And we will check now the analytical solution using G equation calculations of the frame response and the level set approach to handle strong deformations. So why are we doing so? The idea was to say, okay, we've been looking at the flame on a very global point of view, okay, using the simple model. But it's also possible to look at the flame itself, because this G equation gives you the surface as a function of time. So you should be able to look at it very easily. But you need to calculate it using a tool, a calculation tool. And this is what we do in the following. So we will directly describe the surface as a function of G using this equation. And the resolution is based on the flux splitting principle. So I will give some details here, but for two main reasons. The first one is that we've done that quite a long time ago, and also Thierry Schuller was deeply involved in those simulations, much more than me, myself. And so I'll be able to answer a few questions, but if you need the expert, I will put you in relation with Thierry, because he knows this by heart. So we use the level set approach to represent the flame. You don't need, the good surprise is you didn't need a very fine mesh. Of course, grid is enough, as it is shown here. And time was resolved using Runge-Kutta formulations. And you had using the flux splitting principle, you have two things to do: propagation and advection. And we used Ueno schemes here to do so. So simulations are done with Ueno 5 schemes. So what's happening using the simple model? So I should have. Well, that's okay. I should have shown you what's happening for the low frequencies, but you can believe me, for the low frequencies, the situation is properly handled by the code. You get this bulk fluctuation of the flame. The big issue is with higher frequency. So let me remind you that you impose this velocity field. You said the velocity fluctuations were axial and uniform in the flame. And we are dealing here with a situation where you have a 20% fluctuation of the flow, which is already a lot. And when you do so, you quickly realize that this is not working. Okay? You hardly see the modulation. So what's interesting here is that in spite, it's omega star equal to 5, in spite of the fact that you are more or less properly representing the amplitude globally, in fact, you're completely wrong. Okay? It's pure luck that you got the amplitude properly, because you should not, as it is shown here. And this is also the reason why you don't get the phase properly, because the way you represent the flame surface fluctuations, which are associated with those famous heat release fluctuations, are not properly handled by the code. So it is due to the so it's a failure. And is this failure due to the fact that you're using the G equation? There's no reason for that, because it's a perfectly premixed situation. Or is it associated with the flow that you are imposing? Of course, it's the second assumption. So those discrepancies, they may be due to strong assumptions on the velocities. And so we've decided to perform PIV measurements and to impose a realistic description of the velocity fields. So PIV, I'm sorry I didn't put any scheme for that. For PIV, what you do is you use the same flow seeding, and you take two images which are very close to each other, and you look at the particle displacement from one image to the other. And this gives you a displacement, and if you have the time between the two images, you have the velocity. What's interesting compared to LDV is that LDV is punctual, and PIV is you can get 2D images very easily, 2D fields very easily. But if you use realistic description of the velocity field, you won't get analytical solution of the flame transfer function. So we will perform the G equation calculations as we've done before. But for that, you need to propose a realistic modeling of the velocity. So this is what we do here. First, the velocity fields. So this is the case associated with the low frequency. Okay, you had this bulk motion, and I just show one phase of the modulation, it's a given phase. And what you see here is the burner and the flame, and the information is only given in the fresh gases. And we are not looking at what's happening in the burn gases for two reasons. The first one is we are not interested in this information for the model. The other one is because it's much simpler to do so. We used oil droplets, and those oil droplets, they burn when they meet the flame front. Okay, so we only have access to the information in the fresh gases, but it's okay. And what we see is that we have almost no gradient and in axial velocity, and you have small contributions on the radial velocities here, but they are negligible compared to what you get there. So it's validating the assumption on the velocity field, and the trends of the transfer function are correctly reproduced in terms of amplitude and phase, okay? Which is good. Now what's happening in the other case, you remember this pagoda-like flame, so the results are not as clean as the one we get for the flame shape, but this is due to the experimental setup and PID setup. But what you see is that you have large gradients, and also much larger radial velocities than in the other case. So those assumptions were too strong, and the assumptions that we made were too strong on the velocity field, and it's a bad representation of the transfer function. In terms of amplitude, even if we were lucky to find the proper value, and in phase. So I will not spend too much time on this part because it's a bit technical, but it's interesting to see what we did. We say, okay, the key idea is that there is a phase difference of phi between velocity and acoustic modulation, and it depends on y. Y being the actual distance from the burner. So you see what's happening for low frequencies. This variation is small, and the higher the frequency, the stiffer the slope is here. Okay. So what you can assume is that at least at the beginning you have a linear dependency with k, k being the slope of those lines, and there are two ways you can determine k: is by experimental means. You take the slope here, but also you can say it's more or less the convection velocity, the convection vector, and if you take the frequency divided by the mean flow velocity, you can also find k. And we found that those two were very similar. So the phase, meaning that the phase difference is associated with the convection of the perturbation by the flow. So the perturbation is initially acoustics, but as soon as it meets the flame, it becomes a convective perturbation, and then it's propagated along by the flame along the front. So now, how are we going to model the velocity field? We can say that V prime is now not only V0 plus V prime cosinus omega t, as it was before. It's cosinus omega t minus phi here, and phi is given with a linear proportionality with the actual distance to the burner. Okay, the factor here being given by the frequency divided by the mean velocity. So this is not this is different from the assumption we've made before. So the actual field is not uniform anymore, and also you need a radial contribution. And for the radial contribution, we decided to use a very simple assumption. We said, okay, let's use the divergence of the velocity equal to 0 as an assumption, and this gives you the radial velocity as a function of the axial velocity. And it's very easy, you can do it yourself. It's very easy to derive the radial velocity as a function of the axial velocity. You get this relation here. Okay? So there are two last remarks before going to the results. V0 and V prime max are still considered as constant. Okay, so there is still an assumption here, and it seems to be relevant to a certain range of frequencies, but not all the ranges. But you'll see it's still better than what we got before. I have an example, because you can, now that you have those two quantities, you can build the velocity field and compare it to the real velocity field. So you have here experimental results on the left, so the actual velocity as a function of the distance to the burner, and here you have what you've modeled. So I've put here the same. How would you say I've kept all the imperfections coming from the PIV. I kept them to build this shape here. Okay, and what you see is that it's a good representation of the actual velocity field. And in terms of radial velocity field, it's not perfect. In particular, you have contributions here that are not seen experimentally. But anyway, it gives you a first estimate of what's happening in terms of radial contribution very near to the burner, and this is where you need this information. Okay, so it's a good estimation of the evolution of the radial velocity. So it's now time to go to the calculations and see if it's working or not. And this is to show you what we had before, and to remind you that it was not working at all. Now we have another, of course it's much more complicated, and the axial velocity is now depending on the distance to the burner. There is a radial contribution. You don't get access to the amplitude of to the transfer function easily. But if you perform those simulations, what you see is that you now have a representation of the flame wrinkling that is much better than the one you had before. What's very funny is that in that case, you can see pockets here. Those pockets are due to the fact that you pinched the flame, but you still have fresh gases above the pinch, and it burns by itself later. And this is not visible on this particular case, but this is something we also observed experimentally. For higher amplitudes, you pinch the flame and you see those pockets here, exactly as the one you get there. So it's quite nice to see that it's even able to reproduce very fine and precise acoustic flame coupling and interactions. So this is much better. And what's interesting is I can look at the flame surface as on a qualitative point of view, but I can also integrate this flame surface to get the unsteady heat release. And what we see now is on the left the gain, and on the right the phase of the transfer function for this particular case, which is close to the one I showed you before. And in terms of amplitude, you have three experimental cases. The first model we derived, which is called A here, which is the blue line, so which is not so bad but not perfect. And the new model here that was used for several cases, and you clearly see that you reproduce the phenomena much better than before. Okay? So it's already a good point, but it's even more impressive in terms of phase difference, because you clearly see here that for most of the cases you are properly reproducing the phenomena that are occurring on the flame, which was not the case with the simple model, the blue line here. So this tool is able to reproduce quite complex phenomena of interactions between the flame and the acoustic perturbation, the acoustic modulation, for a various range of frequencies. Okay? Even if you don't get the precise value, you get trends which are very well reproduced here. So I think I'm not too bad in terms of timing. Very brief conclusions. So it's a very simplified modeling tool, but it can be helpful for the design of burners. I should mention that it was used, since those flames are close to the one you can get in some boilers, for example. It was used in practical situations. Sorry, I went too far. To help in better designing the burners. In terms of configuration, it's an interesting configuration for the validation of calculation code because it's completely controlled, and it should help you to see the capability of a code, CFD code or other, to simulate interactions. And it should be possible, even if we didn't do it right now, to study other interaction modes like instabilities in LPP burners using this simple representation, or modes, interactions of tangential modes with rocket engine flames, for example. And that's about it. Yep.
I'm also, I can understand this model B in the velocity terms. So you are adding some phase, but
it's a very practical way of seeing it. Okay, but it has also some physical meaning. The idea is to say that maybe I should go there. The idea is to say that as soon as the acoustic modulation is arrived, you have acoustic propagation from the bottom, from the loudspeaker to the top of the burner. But as soon as it encounters the end of the burner rim, then you have a kind of a conversion of the acoustic modulation as a convective modulation of the flow and the flame. And for those range of frequencies, what you can show is that this is the main phenomenon that has to be taken into account. And while pure acoustic waves would propagate as a whole on the flame due to wavelength difference, large wavelengths, and in that case the uniform assumption would be okay. In the case of convection, it's not the case anymore, because this convection is associated with short wavelengths, and you have to take into account the fact that from the bottom of the flame to the top of the flame, the information is propagating with a low speed, which is of the order of the flame speed or of the flow speed, and this has to be taken into account. Acoustic seems instantaneous because it's fast and
model A is just for acoustic products.
Yes.
Okay.
Sorry. Yesterday when I checked those slides, I should have changed those names because they were not used before. A is the first model we derived, the simple one, making the assumption that the flow is uniformly perturbed, and model B is the convective model, the one with the ky factor in it. Okay, sorry about that. So maybe first Camillo, because he raised his hand before.
What is the extension for modeling techniques when the flame is not completely attached to the ring?
So I won't be. It has to remain close to what it's been designed for. I don't think, but this is my personal feeling, maybe I'm wrong, I don't think this can be used for any situation, and I think it's very good at being quick in a case where you have more or less premixed, or at least partially premixed flames, and those flames are somehow attached to a very clear position, because handling flame stabilization on an aerodynamic way, I didn't see any good results on that point. So this is why I was mentioning the boilers. Usually for boilers you have attached flame, the premixing is generally high because you want low NOx flames. So those are situations where this kind of model would be perfect. For the other situations mentioned here, you need to work on it before saying it's going to be okay or not. Well, the reason why I'm mentioning also rocket engines is because usually flames are attached in rocket engine too. So it's but for the other case, I don't know. you had a question too.
Yes, it was about phase diagrams, and shouldn't they be like zero, or this is not?
So phase for pure acoustic propagation, phase should be zero or at least a constant, because the flame should see the same information everywhere at the same instant. You see what I mean?
Yeah.
But since you are transforming the phenomenon from a purely acoustic perturbation to a more or less pure convective perturbation, this convection takes time, and this is what you see. Sorry, I've lost it. This is what you see here. You would expect a kind of a straight line to say, okay, it's a constant time propagation, but it's not constant, but still it's more or less constant, and you get this line. Afterwards, it's a bit more complicated. I could explain it, but it takes some time, so I would prefer not. But for this part, it's a kind of convection time associated with this phase difference. You see what I mean?
Yes, but I'm thinking about extrapolating for zero frequency. It's not experimentally actually possible usually, but this, for very low frequency, you still have this phase difference.
Yeah. True. First response. Yeah. So first response is we have one here. So I don't remember what we get for extrapolation, but this is a good point. I don't want to say anything wrong, so I should just say I don't know and check this afterwards.
And sorry, just
yeah, sure.
Could we use this approach for multiple frames as well?
The thing is, it is always the same. It can do and reproduce thing if you put enough physics in it. If you are talking about multiple flames in terms of flame-flame interactions, that's a good question. I don't know if anybody ever look at what's happening to the G surface when two G surfaces are meeting each other. Huh? This is something you would also very quickly investigate for flame wall interactions, because this is the same idea. What's happening to flame destruction when the flame is encountering another flame or a wall, but I'm not a specialist on that part. There might be some literature, I believe. Some people have looked at that, I think. Yeah.
Just when you have the flame transfer function expression, say, from the simple G equation, what is the interest of having a simpler model attached? Because it's already simple. So done. So
yeah, you're right. Maybe I didn't say this wrong, properly. Sorry. The idea is more first on a pedagogical point of view. It's to say to the students, okay, if you remember your lectures about dynamic systems and first order systems, this really looks like a first order system. And also, but this may not be a good point. Also, if you don't want to be bothered with complicated formulation, it's okay. No, but the first point is more important. It's more to say, okay, if you remember what a first order system is, and usually people do, this is very similar to a first order system. In particular, the fact that it is a low pass filter, it has a cutoff frequency, and so on. I didn't mention the cutoff frequency, but we worked on it, and it's also nice. And It gets, once again, it's pure luck, but it gets the proper cutoff frequency here. So the model is wrong, but it gets relevant information anyway. And it works for a very large number of cases. In terms of amplitude, it's never too bad in terms of amplitude, but the devil is in the details, and sometimes being wrong here can have large consequences in terms of stability. So you don't want this model to be wrong here. Yep.
Is there a physical explanation for the past behavior? Can you explain it in a sort of plausible physical way?
No, if I'm correct me if I'm wrong, but what I said is that this is something that is usually seen, the low pass filter behavior. I wouldn't try to give you a general answer about the question why are most of the flames low pass filters, because I'm not sure there is one universal response to this question. But it's a kind of a statement, and usually flames are low pass filter flames, low pass filters. Yeah.
Is there a difference between your area calculations for the linearized analytical?
No. The difference is they will be associated with the displacement. But once you get this is let me check. Maybe I'm talking too fast. No. Those are the only assumption here is axis symmetry, and this is a classical proportionality between surface and heat release as soon as you are in a permitted situation. So you had to make assumptions here, basically.
What bugs me is that if you go to the high frequencies, then your flame surface is wrinkling
Yes.
in linear case. But if you sum up really the areas, then it should go to the infinity. But in this case, you go to the zero, the low pass filter. So I think there are some different assumptions to get this cosine terms. And
So it's
Is there a different assumption on the one-dimensionality of the profile of Ducruix? Because in the first case we have a derivation of the eta over dr, which is possible only if the curve of the flame is one-dimensional.
Yes.
Otherwise, there's no univoc
it's true.
correspondence
Yes.
between y and r.
This is what we clearly see in the movie. Yeah? Sorry. Here. This is what you're saying.
Yeah. So then, in this case.
You don't need a 1D model here.
But is that an assumption of the equation itself?
I know even in 1D case, you get this low pass filter.
So a first way to give a response to this is we are still talking about a specific range of frequencies. So the very high frequencies you are talking about, we are not dealing with them right now in this particular case. Okay.
But still, even if increasing.
So that's first thing. Second thing is you must remember that you must compare. Wrinkling is not everything. You must compare your flame surface to the mean flame surface. And of course you get more surface on some parts, but you get also less surface on other parts. Okay? Less contributions. And what's happening in that particular case is that compared to the mean flame surface,
I'm thinking it like a rope, and if I bend the rope in that way, it's always getting.
We have flame stretch here, so we cannot stretch a rope, but here.
I think stretching effects are all different.
we didn't.
This is a physical thing, so we're talking about the equations.
But the area calculation is purely mathematical. So if you calculate the area of this blue line, it will always be more than what you get as a line here.
Is there a constraint on that it should remain constant, the area?
No, there's no.
Because if you always wrinkle, the area is always getting higher.
The thing is,
Diminish the heights and
yes,
so
yes.
the width is constant, diminish the height, well you can get
Yeah.
the wrinkles that
Yeah, you have, right, maybe I didn't say this right, but he did it better than I did. You have to, this is what I was saying when I said you have to compare to the mean, and the mean is, for example, from here to there, and what you are comparing is, so of course you are ranking on the frame, but you also modify the whole profile. So you have to integrate it and see what it is compared to the profile of
But this is a non-linear version of G equation. So
it's not linearized. It's not linearized. It's a complete set of equations. Yep.
Yeah, and since it just came up, this is stretch effects.
So we did some work where we included some stretch effect, and also you have papers from Leuven's team working a lot on those aspects, trying to see if it was and what they show is that if you go higher in the frequencies, you have wrinkles that looks like cusps a little bit, and in that case you have to take into account some stretch and strain effects, curvature and strain effects, because you strongly modify the flame propagation speed, but this is for those, if I remember well, for those frames it's a kind of conservative effect, meaning that it will burn faster than, you see what I mean? It will lower the wrinkles because it will consume the wrinkles faster. But this may depend on the situation. But you're right.
It's very interesting that with all these assumptions, we still get what we should get.
At least at first order. If you look into the details, it's not that perfect. Yep.
Before I was saying that actually in this case we have a different profile. So
Yes.
do we leave some of the initial assumptions on the equations?
So I'm not sure I got it well. There's no assumption on the velocity is much more complex. The velocity field is much more complex than the one we had before, which was uniform and actual. And but we kept we kept the assumption on the flame speed, but it would be not too difficult to include a flame speed depending on curvature or strain. It can be calculated.
Because I was referring to the initial equation in which there is this
Yes.
derivation of the eta over
Yes.
the radial. And so in that case,
So what? Say it again. Let me go back to the slide you're mentioning. Are you talking about this one? Huh? Here. Is this the one?
Yeah.
And what you're asking is?
In this case, how do you treat the term the eta over the r?
I think the plot is not that function. It's for G equation because we have 2 dimensions. In this case, I think it's 1 dimension.
Yeah, but then
You may have, in the assumptions, maybe, I should have put the assumption concerning eta here. You're right, it should have been there.
is this just for a mean profile or for also for?
No, what we are, I think we are saying the same. What we are saying is that you already have made the assumption here that eta is a function of R and on R only. You can't get those. You're right. There's already an assumption here. There's a bijection between eta and R, and you cannot have 2 eta for 1 R and so on. You can't have those tricky curves, which is not the case here because here you just calculate the whole equation. Yeah, maybe a last one. I don't know if we don't want to get too late compared to the program. I know there was a last one, but I was saying maybe that's the last one.
Could you just a little bit elaborate on this conversion of the acoustic wave to the convective? Does it happen if there is no fringe, just air?
Yeah, we've done. This is a kind of adaptation of the acoustic to the open jet flow, and we've done several years ago with Daniel Ducruix. We've done measurements on the same kind of convergent nozzle, and what we could show, if I remember well, is that you have three types of responses depending on a comparison between the frequency of the modulation and the jet sensitivity. If you are very far away from the jet sensitivity, meaning the jet natural frequencies, propagation will be purely acoustics, and you will have very nice acoustic fronts and a constant phase and everything. Then you have a kind of a mixed region where you start with an acoustic propagation, but then you're transferring to the jet. And if you are very close to the jet natural frequencies, then you directly, in fact, you directly excite the jet, which responds very quickly, and then the modulation you see is much higher on the convective point of view. The acoustic modulation is still there somewhere behind, but you've excited so in such a strong way the jet that what you clearly see is the convection of the perturbation by the jet, because it has been associated with the natural frequency of the jet. That's more or less the idea, and it's a bit different with combustion. It's a bit more complicated, but those ideas are still similar. Thank you.